Once again, I'm sorry because I didn't have my solution with me. So I might make a mistake somewhere. So please double check. Someone with calculator, can you please calculate the value?
Tidur ngantuk tu.
So what is A1?
Mak kena set
Wah,
function pun.
leceh ni nak pakai calculator ni. Please someone.
4 metric Newton.
Is anybody doing it? Sebenarnya begini.
Jauh tu. Satu kosong satu kosong negatif satu satu satu
Okay, let me do this lah. Pelan-pelan just bear with me for 2 minutes.
satu negatif
Tak ada
dua
orang nak buat untuk saya.
satu dua dia ada negatif satu angka bagi saya banyak bagi awak lagi sikit satu tujuh satu kosong kosong baru je S nampak cakap lah bodoh kita is it A1 0.5
Okay, hopefully I should get this right. Okay. I don't know if you can see this. Boleh nampak tak? Okay, saya guna reduce row echelon form ataupun Gauss-Jordan elimination. So from Gauss-Jordan elimination, what I get here is A1 equal to half B1 equal to minus 3/4 and C1 equal to 0 and B1 equal to 1/4. Okay, so inilah jawapan saya. Jawapan saya lah. Okay, hopefully you can see kita bisa skill saya besar sikit lah. Alright, okay, so that's how I did this one. So hopefully it's the same value that we get. Okay, half minus 3/4 0 and 1. Okay, sama. So if you can do for H1, you can do the same thing for H2, H3 and H4. Okay, so now our H1 becomes this. Just plug in all the values. I think C1 is 0, so that's why there's no Z square here. There's no Z square here. And this is how we get it. So I'm showing you how to get that one. Okay, so the rest, H2, H3, and H4, I think you can do it on your own. Right? So
I got
ada sikit lagi yang complicated di sini. If you look at this, can you see the K matrix? Okay, we use this potential energy. Remember our bar element? Remember our bar element and our thrust element? How do you find the K stiffness matrix?
bar
For element, element matrix. Element stiffness matrix. So we use energy then. We use potential energy. So this is the same thing here. Note that we have to integrate from minus 1 to 1. Basically, this is the limit. Where the limit, remember for our element, the limit, the lowest is minus 1 G and plus 1 Z. And this is why the limit is from minus 1 to plus 1. And you integrate this, you should get this graph. Of course, remember that this one here is EI over L cubed here. pi over L cubed, and plus 8 is missing. So this is just algebra. Note, this is a very tedious process, but once you can do it, then which means you understand all the steps, all the steps. You understand all the steps. You
OLM.
understand all the steps. Okay, can you imagine? Can you imagine? This is a 4. This is a 4 by 4, right? This is a 4 by 4, which means we have our beam element. We have P1, P2, P3, and P4. Okay, so we have 4 degrees of freedom per element. But for frame element, the K matrix will be a 6 by 6,
Fuck, asal lah.
which means it has 3 degrees of freedom per node. I think I mentioned that. Here. Okay, so frame, one dimensional element with 3 degrees of freedom per node. So note that it's a combination of beam and bar element. 1 degree of freedom will come from the bar, while for truss element, not for truss element, for frame element, what we have here, okay, note that it is tilted at an angle. So note that when you have a inclined angle, means that there's a transformation matrix involved. Remember, for our truss element,
LM.
we have Lm 0 0 0 0
LM.
Lm, right? For frame element, we also have our transformation
Habis
matrix,
banyak ah.
which is, if I'm not mistaken, is lama, saya dah lupa lah. If I'm not mistaken, note that in our case, for
3 by 3.
for our frame element, it's a 6 by 6 matrix. So what we have here, if I'm not mistaken,
12 by 12.
I cannot recall. And then we have 0 0 0 0 0 1. This is just for the first node, the first node, because the first node we have 3 degrees of freedom. So that is why we have a
Dah 6 eh.
oh,
Itu
this is not
5.
right. This is not right. I'm sorry. I think it should be cosine and sine, not this one. So what we have here, it should be a 6 by 6 matrix. So 2 is for the beam.
Banyak.
1 here is for the 1 here for the bar. For the so for the frame, let me show you what I meant here. For the frame is that we have this additional, and of course we have our rotation, and we have our this one here. So that's why we have 3 degrees of freedom. 3 degrees of freedom. So I think I'll talk more about frame later when we get into it. But just note, the approach is the same. From your bar element, the approach is still the same, but note that the level of difficulty becomes harder and harder. So this is my recommendation. Please make sure you really understand your bar element, and that is one of the reasons. Everything must be solved in terms of A, in terms of A0, L, and E. Why? Because I know UTM student ni dia they are more like human calculator, which is what we do not want. What we want is that you must be able to think, and that is one of the reasons there's no numbers involved. Everything in terms of variables. In terms of variables. Okay, so this is the element. This is the frame element. Alright, so now we are done with the element stiffness matrix. Then we can go to the force vector for distributed load. Note that for beam, we have this kind of loading. We have distributed load, we
Distributed,
have
concentrated,
point load, and we have point
point,
moment.
moment.
There are three types of uh, loadings here. Note that because distributed load is happening on R on this certain length, which means it will involve the elements. So that is why we need to find this thing here. Okay, what we call the force vector for distributed load. Okay, at an element, at one element. But for point load, uh, point moment, it is applied at our global level once we assemble the matrix. Okay, once we assemble the matrix, because point only involves the node point. Okay, node point. But if you have distributed load along a line, which means it will involve an element or elements. Okay, so please take note of that. Take note of that. Okay. Okay, so this is the model, finite element model for this distributed load. For distributed load. Okay, so finally we are done. We know what is the moment, we know what is the shear force, and then you apply everything that you have derived to this. And I think this is a good exercise for you to do it manually and to compare this with anything. To compare this with anything. I think my video is talking about this. My video, I think my video, this video here, if I'm not mistaken, BIM demo here, this one is based on this question. Okay, it's based on this question. Okay, so I think I'm going to stop here. Okay, I lost my voice because I have PC problem, I have mic problem, a lot of things today this morning. Okay, so I think I'm going to stop here. You have 1 hour extra here, which you can use, to continue your assignment number 6. Assignment number 6. So I've given you all the clues, so hopefully you can continue whatever I told you just now. Okay?